In the previous session we were talking about breaking up a problem into parts and trying to solve each part separately, individually. A kind of divide and conquer type approach to finding proofs. Now some proofs virtually demand that. Especially the kind the if and only if, and we're talking about that at the very end of the previous session. Now typically an if and only if type problem is presented in the following way, well, a theorem statement. So you have some mathematical statement, P, whatever that is, quite general, and you have another one, Q, and your theorem statement will be of this form, that P is true if and only if Q is true, and that can be shortened to PIFF, so if and only if, or if, so P if of Q. Okay. Now, what does that mean? If you see something like this, especially of this form, now it's shorthand actually for two statements. You have to actually prove two things. It's a two-headed, two-part statement. One part of it is P only if Q, and the other part is P if Q. So there are two parts. Right? So you have to do two proofs to do this. So always when you have an if and only if type theorem statement, you know that you're going to have to do two proofs. And often one of those two is easier than the other. I'll come back to that. I'll mention that again a bit later. All right. So now it's not mentioned in this text, but there's pretty strong convention in pure mathematics, at least. And remember, one of the things I'm trying to do in deGarisMPC is to get you as familiar in pure math as math physics. And some computer courses thrown in, including this one, which is the first. So, but my goal is is to get you as fluent in the language of pure math as math physics. And as math physicists, one of your tasks, if you follow me right through for years, is to think about the enormous implications of quantum computing when it comes, particularly topological quantum computing. And to understand that, you'll need a lot of math physics. Now, I've talked about this several times, so I won't go into that again. Alright, so if you're a pure mathematician, if you say something like this, or usually P if Q, you know you have to prove it both ways. So you have to prove P only if Q, and you also have to prove P if Q. So one's one way and one's the other way. And the pure math convention is you do the only... hold on, I don't remember. It's been a while. Which one goes first? I think it's from right to left. So you start with Q and hence prove P. And this textbook, I think, goes the other way. So now look, I assume the author, Sipser, is not a pure mathematician. He's probably more a computer science guy with strong mathematical ability. But he's not following the usual convention for of the pure mathematicians. Now you may say, so what? Who cares which order it goes? Well, it's just sort of annoying. I mean, if you're accustomed when you're reading pure math proofs in pure math books, that from Q to P, from the right hand side to the left hand side, so you start with and then prove that. If that's the convention that you do that first, it's sort of annoying to realise, oh, they've gone the other way. Damn. So so be aware that the pure mathematicians tend to go from the right hand side to the left hand side first. So that's the first part of the proof, and then they go the other way, from the left-hand side to the right-hand side, so from P to Q. Okay, so remember, so you see this, and you know you've got a two-part proof. You have to show two things. One is you have to prove P only if Q, and you also have to prove if P then Q. So the two parts. Now, what does this mean actually? So P only if Q. So analyze that a little bit. What does it mean? It means that P is true only if Q is true. So the only way P can be true is if Q is true. Okay? So if you get P, you must have had Q, right? If you don't follow it, rewind. That's rewinding is the great beauty of video lectures. One of the enormous superiorities over classroom lectures, because the professor really only says things once, usually. And if a student is distracted, thinking about the great time he had with his girlfriend, boyfriend previous night, and attention is distracted, staring out the window or whatever, so if the student misses something, well, that's it, right? Doesn't get a chance to go back. It's just lost on that student. Whereas with video lectures, if you don't follow something, just rewind. Go back and play it again until you get it, hopefully. Right? Okay, so P is true only if Q is true. So if you do have P, you know you must have had Q. Okay? So you can rewrite that. Instead of P only if Q is P arrow Q. So if P is true, Q is true. Or is it the other way around? Hold on. It's been a while. Let me think. P only if Q. Alright, let's think of it, because the alternative is this. So, alright. Okay, so an equivalent way of writing this, P only if Q, is just P arrow Q. So if P is true, then Q is true. So if you got P, you must have had Q. Right, so, okay. Now the second part is just the if. Here's the only if. So there's like two parts, remember. So if P is true, then Q is... hold on. P if Q. That's a way of saying that if Q is true, then P. P is true if Q is true. So start with Q, and then you'll get P. Right? So this is another way of writing this. And you put these two together, and you get this form. The only if and the if combined. So P is true if and only if Q. And you can split that up into that and to that, and then you can rewrite this as that, and you can rewrite that as that. So in other words, when you see this, you have to prove two things. If P, then Q, and if Q, then P. Now, if you want to conform to the usual convention of pure mathematicians, then you usually go from the right-hand side to the left first. So, in other words, this one. See? So he's got like the second part. Pure mathematicians would make it the first part. Alright? Okay. So, well, there's certain logic to his method. If P then Q, then that's looked on as the forward direction. So you're going that way. I guess going to the right is considered forward. Right? So from P to Q, going this way is considered the forward direction, and going the other way. So from Q to P, you can rewrite this as this, right? So you're going from Q to P, given the arrows, so from Q to P, the arrow's going that way, So you can look on that as the reverse direction. Okay? Now, if you're thinking in terms of arrows, so from P to Q arrow this way, from P to Q arrow that way, from Q to P arrow this way. So you can combine these two arrows and get this sort of double arrow like this. So P double arrow Q is an alternative way of writing this. Okay? Because you've got to prove it in two directions. So if P then Q, and if Q then P. You have to prove it both ways. And P and Q, they are mathematical statements. That'll become clearer as we start doing a lot more proofs further into the text. In fact, this board, so these 4 sessions, we will start doing some actual proofs, proper proofs. So you'll get a hang, you'll get familiar with how this kind of thing is done. All right. So you see that, you can think of that as this, and you need to make 2 proofs in one direction and the other, the forward direction and the backward direction. So if P then Q, and if Q then P. It's just a bit of controversy about which one do you do first. Well, pure mathematicians go from right to left. So they would start with Q and then prove P, and then they would, in the second step, they'd start with P and then prove Q. Alright, now I mentioned that a little bit before. Typically in an if and only if type proof, or theorem statement, one direction is harder to prove than the other. That's sort of almost common sense. It's highly unlikely that they're both of equal difficulty. It's much more likely that one will be harder than the other, just on a priori probability grounds, right? Okay, now so that's sort of an end of a subtopic here. Now, what we're going to do here in these few lines is mention another kind of proof technique, I guess, where you're talking multi-part, a two-part, in this case, again, a two-part proof, is in the context when you're told, let's say in the proof statement, the theorem statement, you're told that 2 sets, A and B, are equal, and you're asked to prove that. Like the theorem statement might be set A is equal to set B, where when you're told what those 2 sets are, we're talking in the abstract form. Okay, so if you're told that set A equals set B, so in other words all the members correspond 1 to 1. The 2 sets have the same members, in other words. Okay, then how do you go about proving that 2 sets are equal? And let's see, 2 sessions from now, we will actually do a proof of this kind, showing that 2 sets are equal. And now, how do you go about doing that? Well,